Bismillahirrahmanirrahim. Today our next topic name is Fourier sine and cosine series. It is our lecture number 13. So I am writing here a Fourier cosine and sine series. Our efforts in finding the a0, an and bn significantly reduce if we find the nature of the function, either it is even or odd. How we can reduce the efforts that we solving a0, an and bn, because it becomes very lengthy here. We have to find all these coefficients. If we find the nature of the function, either it is even or odd, then you only find an and a0 and an, or only bn. It is only possible when you find the nature of the when you are familiar with the nature of the function. So how we can familiar the nature of the function? You very well know that if the function is called an even function, a function is called an even function if f of minus x is equal to f of x. F of minus x is equal to f of x. And in this way our examples are, example number 1, cos minus x is equal to cos x. And you know that cos, if there is a negative sign in the angle of cosine, then it becomes positive. In this way, even function f minus x whole raised to the power square, it is equal to x square, minus x whole raised to the power 2 is equal to x square. Similarly, a function is said to be an odd function if f of minus x is equal to minus f of x. A function is said to be an odd function if f of minus x is equal to minus f of x. And in this regard, the examples are sine minus x is equal to minus sine of x, and then minus x whole raised to the power cube is equal to minus x cube. So you see here a function which does not fulfill the said above criteria. A function which does not fulfill the said above criteria is called neither even nor odd. Neither even nor odd. So in this way our example is exponential function. So in trigonometric functions, sine, cosine, and we take another e raised to the power x mean exponential function. Cos is a even function, sine is an odd function, and exponential neither even nor odd. So I take some more examples here, some more facts about even and odd functions. Even functions are symmetric about y-axis. Even functions are symmetric about y-axis. So in this way examples are f of x is equal to x square, and its graph is in this way, like a upward parabola, because intervals are on the real line is infinite. So at every periodic interval its shape repeats itself. The shape of the function repeats itself. So another function, that is f of x is equal to mod x, and you know that it is an even function. It is an even function. If I substitute here at the place of x negative x, you see here negative x mod is equal to positive x, is equal to mod of the x, and the graph of this function is in this way. You can draw this, and if you take more and more points on this line, you get different types of the same type of graph at different points. The same type of graph at different points. In our engineering or physical sciences department, we see you are very familiar with AC circuits and DC circuits, AC motors and DC motors. Here you see alternating current and then half wave rectifier, and this type of examples relate with physics and electronics. Here the DC motors are, in this way we only have the positive cycles. We have only the positive cycle, the results obtained only for the positive cycles. Here the second type is odd functions are symmetric. Odd functions are symmetric about origin. Odd functions are symmetric about origin. If we take a 180-degree turn, the functions reshape itself. The function reshape itself. The odd functions are symmetric about origin, or we say it is 180-degree rotation. It takes 180-degree rotation. If you rotate the body about 180 degree, it takes the same shape of the original function. Here the examples of the odd functions are, example, f of x is equal to x and its graph is in this way. In this graph is in this way. If I if you see here, if I take a 180-degree angle in this way, this side comes here and this side comes here, and this is again the same line. This is again the same line. When you rotate this side, when you rotate at 180 degree, this side comes to this and this side comes to this, and we get again the same function. And you say that and you see here it is symmetric about the origin. It is symmetric about the origin. Another example is f of x is equal to x cube. F of x is equal to x cube. Here the graph of x cube is this. If you again rotate this, if you rotate this graph about 180 degree, this upper side come to this side and this lower side goes to this upper side, and you see that this graph, when you rotate at 180 degree, it gives the same shape. It gives the same shape here. And I take another example relating to a piecewise function, that is -1 to and 1. -1 lies in the interval -pi to 0, and then the value of the function is 1 from 0 to pi. And you see here I take intervals from -pi to 0. This is 0. This is 0. And from 0 to pi. And you see here -pi to 0. -pi to 0. The function value is -1, so I draw a line from -pi to 0 in this way, parallel to -1. And from 0 to pi I draw a line 1 from 0 to pi. Such type of functions show their nature, that is odd. If a graph is in this form, then it shows it shows the odd behavior. It shows the odd behavior. So I take another example, that is AC generators. As you see here, it is a sine wave, sinusoidal wave. Here this half is positive and this half is negative. But in DC generator you see only positive half appears. Negative whenever a negative half appear, it shows a negative value there, zero value there. So AC generators, it has or you say AC current, it has a pulse positive, then negative, then positive, then negative. So in this way it shows an odd functions behavior. and odd functions behavior. First positive, then negative, then positive, then negative. When a graph exhibits such type of properties, then we relate it with the odd functions behavior. Now, some properties of even and or odd functions. The product of two even. The first one is the product of two even function is even. Let's suppose f of x and g of x are two even functions. Let me suppose that f of x and g of x are two even functions, and they fulfill the property that we define above. F of minus x is equal to f of x and g of minus x is equal to g of x. Now I am describing here, then f of minus x is equal to f of x and g of minus x is equal to g of x. Now we see their product is f of x is equal to f of x and g of x. This f of x shows the product of these two even functions. Now I replace this x with negative x. I replace this x with negative x. So I am substituting here f of minus x is equal to f of minus x, g of minus x. And you know that, and you see here f of minus x is equal to this f of x. So you see here f of x. I am writing this f of minus x is equal to f of x, and g of minus x is equal to g of x. And you see here f of x, g of x is equal to f of x. So I am writing here f of x. So in this way, you see here, this is the definition of even function. This proves the definition of even function. So we say that the product of two even function gives the even result. The product of two even function gives the even result. So now this shows that the product of two even function is even. This shows that the product of two even functions is even. Now the second is the product of two odd functions are even. The product of two odd functions are even. Let me suppose that f of x and g of x are odd functions. Let me suppose that f of x and g of x are odd functions. Then f of minus x, by definition, f of minus x is equal to minus f of x and g of minus x is equal to minus g of x. This is the definition of the odd function f of minus x is equal to minus f of x and g of minus x is equal to minus g of x. Now we define the product of f and g as f of x is equal to f of x and g of x. And you know that we disturb the domain of these functions. Here we substitute minus x at the place of this x. I am doing here f of minus x is equal to f of minus x, g of minus x. And you know that f of minus x is equal to minus f of x and g of minus x is equal to minus g of x. So you substitute here at the place of f of minus x is equal to minus f of x, and at the place of g of minus x is equal to minus g of x. When you multiply this negative sign, when you multiply, it gets positive. So our answer is f of x, g of x. And you know that f of x, g of x is equal to f of x. So f of minus x is equal to f of x. So in this way, it fulfills the definition of even function. So when two odd functions multiplied with each other, you get even function. When the product of two odd functions gives even function as a result. Now we move toward the third result, that is the product of an even function and an odd function is odd. The product of an even function and an odd function is an odd function. So let f of x is even function and g of x is odd function. It is up to you. Either you choose f of x as odd function and g of x as even function. So at this time I am taking f of x as even function and g of x as an odd function. So then f of x minus x is equal to f of x, because I am saying f of x is even, and g of x is odd, so g of minus x is equal to minus g of x. Now I am defining their product. F of x is equal to f of x g of x. Now I change its domain x by minus x. So f minus x is equal to f of minus x is equal to f of minus x into g of minus x. And you know that f of x is an even function, so f of minus x is equal to f of x, and g of minus x is equal to minus g of x. When you multiply these two, you get minus f of x gx, and this f of x g of x is equal to capital F of x. So this is minus f of x. This proves the definition of odd function. This proves the definition of odd function. Now we prove here two more important results. That how we can reduce our work if the interval is if our interval is periodic. How we can reduce our work. So, and these results we use in reshaping the Fourier coefficients. In reshaping the Fourier coefficient, and how we can reduce our efforts, and we see in inshallah in our next lecture. Show that minus a to a f of x dx is equal to 2 times from 0 to a f of x dx, and when f of x is even. When f of x is even, it is more important here to remember this, that our function is even. So I take the left hand side. Left hand side is equal to minus a to a f of x dx. So I use the property there. I split the integral from minus a to 0 f of x dx plus from 0 to a f of x dx. This side is according to our required result. So I am replacing their places, interchange their places. That is from 0 to a f of x dx plus from minus a to f of x dx. So I am not disturbing this. I am not disturbing this integral. I just try to reshape this integral like this. I try to reshape this integral like this. When this integral becomes take the shape like this, then it becomes 2 times. So I say this is equation number 1, and let I is equal to from minus a to 0 f of x dx. Let I take this is equal to I is equal to from minus a to 0 f of x dx. Now I substitute x is equal to minus u. X is equal to minus u. Then take differential dx is equal to minus du. So in this way I have to change its limit also. When x is equal to minus a, this lower limit, when x is equal to minus a, and when you substitute this x is equal to minus a here, x is equal to minus a here, then negative sign cancel with negative sign, then u is equal to a. When you take x is equal to minus a, when you substitute here x is equal to minus a here, negative sign is cancelled with this negative sign, you get u is equal to a. When x is equal to 0, the second limit, when x is equal to 0, when you substitute x is equal to 0 here, then u is equal to 0. Now I substitute this changing, I make this substitution here. I is equal to from a to 0, and you know that from when x is equal to minus a, when x is equal to minus a, u is equal to a. So this negative a changes by, replaced by a, so it is a to 0. Then f of here x is equal to minus u, I replace x with negative u, f of minus u, and then dx is equal to minus du, and you see here this is minus du. With this negative sign, it is a property that you can interchange the order of the integral. Interchange the order of the integral with the negative sign. So I interchange the order of this integral here. I take from 0 to a with this negative sign. With the help of this negative sign, I change its order, the limit order. From 0 to a, f of minus u du. Since we know that the function is an even function, so f of minus u is equal to f of u. So from 0 to a, f of u du. From 0 to a, f of u du. And one thing you must kept in your mind, that these are the dummy variables, x, y, z, u, whatever the values are. So these are the dummy variables. So you can change this u with x. There is no difference here. So 0 to a, f of x, d of x. So in this way, I is equal to from 0 to a, f of x, dx. Now you substitute this value of I in equation number 1. Equation number 1 implies from minus a to a, f of x, d of x is equal to 0 to a, f of x, dx plus 0 to a, f of x, dx. So in this way, when you add them, it becomes 2 times from 0 to a, f of x, dx. 0 to a, f of x, dx. So it is a proof. It is a proof when function is an even function. When function is an even function. Now we take another result in which we show that from minus a to a, f of x dx is equal to 0 when f of x is an odd function. When f of x is an odd function. So left hand side is equal to minus a to a, f of x dx. I split the integral from minus a to 0, f of x dx plus from 0 to a, f of x dx. Again, I am doing here from 0 to a, f of x dx plus minus a to 0, f of x dx. Again, I am changing the places of the integral. First as the place of second and second at the place of first. And I name it equation number 2. Let this second integral is equal to j. From minus a to 0, f of x dx. Again I make a substitution here. Let x is equal to minus u. Then dx is equal to minus du. When x is equal to minus a. When you substitute this x is equal to minus a, this is minus a. When you take x is equal to minus a, here this negative sign cancel with negative, so u is equal to a. When x is equal to 0, then u is equal to 0. So j is equal to, as you see here, minus a becomes a and 0 is equal to 0, and f of, I substitute this x is equal to minus u, f of minus u, and then dx is equal to minus du, as you see here. So I take this negative sign outside the integral. I take this negative sign outside the integral. It becomes from a to 0, f of minus u du. And with this negative sign, what happens? I interchange the order of the limits. I interchange the order of the limits, or reverse the order of the limits. This becomes 0 to a, f of minus u du. Since we know that function is an odd function, so according to the definition of the odd function, f of minus u is equal to minus f of u. So I substitute here 0 to a minus f of u du. I take this negative sign outside, and earlier I said you that this x, y, z and u are the dummy variables. You change them with each other. So 0 to a, f of x dx. So equation number 2 implies minus a to a, f of x dx from 0 to a, f of x dx plus, and the value of j is from 0 to a minus from 0 to a, f of x dx is equal to 0 to a, f of x dx minus 0 to a, f of x dx. this integral is cancelled with this integral and you get equal to 0. And inshallah ta'ala we will see how we can change the Fourier coefficients by using this idea of even and odd functions, and how we can reduce our efforts in calculating the Fourier series regarding sine and cosine. Inshallah ta'ala we will meet regarding that in the next video. Till then, take care. Allah Hafiz.